Today, I would like to discuss about compound noise factor. Before I start, let's try to think about what is the cross orthogonal array experiment. If you are using cross array experiment, then the total number of experiment will be the product of inner array and outer array. Here we put the control factors in one orthogonal array. We call it inner array. And we put all the important noise factors in another array. We call this outer orthogonal array. So for each design, we call the combination in inner array is a design. We need to do some samples. And we are using outer array to do the samples. So for each design, we will go through the outer array. In this case, if you are using L36 as an inner array, and in this case, we are using L8 as an outer array. So for each design, we need to do 8 samples. And these 8 particular samples are according to the combination of the noise factors arranged in the outer array. From that 8 samples, we will compute or we will estimate the SN ratio. So one design need to go through 8 samples in this case. Therefore, if we have 36 designs, the total number of experiments we need for this cross array experiment will be 36 multiplied by 8, which is 288 samples, which is quite a lot. Although we already reduced the number of samples in the outer array to kind of try to do a balance and a symmetric samples. So we can understand what is the influence of the noise factors. However, there are still a lot of experiments need to be done if we are using this cross array experiment. Using the cantilever beam as an example. In the classroom example, we use 4 control factors. Over here, 4 control factors, E, B, H, L. And here we only consider 3 noise factors. This is our 4 control factors arranged in L9. And this is 3-dimensional torus, and we arrange that in a L4 orthogonal array. So the total number of experiments will be arranged in this format. Here, this is inner array, and this outer array, we kind of move it upward and do a transpose. So it will be easier to get these 4 samples, which is affected by the combination of these 3 noise factors. And the level, the factorial level for each noise factors are specified over here. So we can get 1 sample, 2, 3, 4. In this case, L9 by L4, the total number will be 36 experiments. However, remember the example I asked you to do during the in-class practice. We try to consider 4 noise factors. This is another example. We ask you to consider 4 noise factors right here. Still, we have 4 control factors, which is arranged in L9. But the outer array, because we are using 4 noise factors, L4 is not big enough. So we need to go to a bigger outer array, which is L8, right? So the cross array design need to use L9 by L8, which the total number will come to 72 experiments. Compare with the previous example. In previous example, we only consider 3 noise. So we just need 36, only half. Then you can understand what is the reason why I use 3 noise factor at the beginning. Because if you consider too many noise factors, the outer array will increase which will increase the total number of experiments. In this example, if you are considered 4 noise, then the total number of experiments will be doubled, which means that you need to pay twice the money or need to spend twice the time to do the experiment. Excuse me. Cross-array experiment is very effective, and ideally it is very good because we can put the control factors in inner array and arrange all the noise factors in the outer array. From the outer array, we can have a very good symmetric balanced samples to understand what will be the influence of these noise factors. However, it is still too expensive. If you are talking about experiment cost is very high, such as the IC production, you need to do a lot of semiconductor process. Therefore, the boss or you would like to think of, is it possible to further reduce the number of outer array samples? Outer array sample is very efficiency already compared with random samples, which didn't consider the actual influence of the noise. Therefore, the estimation of the signal to noise ratio will not be accurate. Outer array good, but too expensive, too many experiments. Is there any way we can reduce the number of experiments? Which come to the topic we would like to discuss today, which is compound noise factor. Because they are noise factors, the output value will not be right on the target, just like the cantilever beam example, right? Under the influence of the tolerance, the actual value of the dimension will be different. Sometimes the value will be on the upper bound. The output value will have a upper bound, largest value. Sometimes you go to the smallest value, depending on the distribution. So we are thinking why the output will go to the upper bound. Because under certain combination of the noise factors, which will make the output push it to the largest. And sometimes the some particular combination of these noise factors will make your output go to the lowest. And if there is no error at all, there's no noise factors at all, your output should right in the middle, nominal value. Therefore, it gives the engineer some inspiration, some ideas. Is it possible we just first find out what kind of combination for the noise factor will be, and which will make the output to the lowest? And this kind of a combination, we put it together. We call this combination is a compound noise. At the same time, we can find a combination of the noise factors. In such a way, we'll push the output to the highest. Then we call it level 3. Level 1, lowest. Level 3, highest. How about level 2? Level 2, we just make our factors right at the nominal value, which means that no errors at all. So we will have several combinations. One combination of the noise factors will make our output to the largest, 最大的. One combination will make our output to the lowest, 最小的. So if we can only make 3 samples, which we will understand these samples will be the largest, will produce the largest output. Another sample will be the lowest output. So we can, from these 2 samples, understand what will be the output range, right? From this output range, if we want another samples, we make it in the middle, which is level 2. So from these 2 samples or 3 samples, we can have a basic idea about what will be the output distribution for this design. Then we can use these 3 particular samples or two samples. Depends on you want to make it 2-level or 3-level. And using these 3 samples or 2 samples to estimate the SN ratio for each design. Then we can have a good estimation of the inference for the noise factors. At the meantime, reduce the number of experiments. Let's look at this one example. This is a bathroom scale. If you have this experience, or you can try to practice at home, you'll find out the weight you get will depend on 2 different types of noise factors. The first one is the type of floor your bathroom scale is sitting on. It could be a hardwood, like this one, hardwood, or it could be a thick carpet. And you will find out that the bathroom scale, if you put it in the hardwood, or if you are using that in the thick carpet, your weight will be different. If you put the scale on the hardwood, will be slightly larger than the weight if you put your scale on the thick carpet. This is a noise, right? What kind of noise factors in this case? We know we have 3 types of noise factor, right? We have outer, we have inner, and we have manufacturing. N is which type of noise factors? Carpet, hardwood. Which type of noise factors? Yes, outer. Because this is not related to the product itself. It's related to the outside of the product. And here, different type of flow is one of the application environment. Therefore, type of flow is a noise factor which belongs to outer noise factors. Second noise factor is the position you stand on the bathroom scale. You can either stand in the middle or you can stand on the side. And you find out that if you stand in the middle, the weight you get will be heavier. But if you stand on the side, then will be lower. So in this case, if we consider only these 2 noise factors, one is the type of flow. The second one is how the user stand, where the user stand on the scale. And we already know the inference direction. Therefore, can we come up a combination of this flow and position? For this particular position, which means that if you put it on the thick carpet, and also if you stand on the edge, O2 is on the edge, then your reading, your bathroom weight you get will be the lowest, right? This one will be the smallest. On the other way, if you stand in the center and one and also put the scale on the hardwood, then you will have a reading the largest. Because if you put on hardwood, the reading will be increased, and also you stand in the middle, the reading will increase too. So if you put in the hardwood and stand in the middle, during this combination of the noise factors, your weight get from the bathroom scale will have the largest reading, largest output. So this is 2 combinations. One combination will make, this combination is a combination of 2 noise factors, type of flow and the standing position. Under this combination, your reading, your result get from the bathroom scale will give you the lowest weight. On the other way, if you on this combination, it will give you the largest weight. So we call this combination a compound noise. It's a combination of several noise factors. How about this case? we designed the cantilever beam. And in the classroom example, we consider 3 noise. Remember which 3 noise? The machining error of the height, of the length, and also the thickness, the width, sorry, the width. So we consider 3 noise. And we were putting that in L4, remember? But if we know the inference of each noise factor, we know if the delta H is on the higher level, which is plus delta H, minus delta H, the inference to the output, to the stiffness will be this way. Again, at the same time, the length, the inverse of length on the output will be this direction. This is analysis of mean. This is effect plot. In this case, we are using the effect plot on the noise factors instead. And the inference of the noise factor delta B will be this way. So if we make a combination delta H1, delta L2, and delta B1, such this one, which will make our stiffness to be the lowest, remember? On the same time, how about CF2? Then you can see under another combination of noise factors, H2, L1, and B2, the output K will become the largest, will have the largest, because B in level 2 will be increased by the terms, increase, decrease, increase, the denominator decrease, the K will be the largest. Therefore, you can see in this case, we can use 2 combinations to find out what will be the upper bound of the output distribution and also the lower bound for the output distribution. This is how compound noise factors work. How do you know the direction of the noise factors? Well, how do we know the direction of the control factors? We are using analysis of mean to have the response table, to have the effect plot. So we will know the inference of the control factors. On the same time, using the similar concept, we can use analysis of mean on the noise factor. Then we can understand what will be the inference of the noise factor, right? Let's look at the example we were working on for the cantilever beam. This is L9 by L4. And in the past, L4 is an orthogonal array. And this orthogonal array, we need to use this orthogonal array for every design. But can we just apply this outer array to only one design? For instance, to the first design. From the first design, we will have 4 output under the inference of 3 noise factors. So we put it out and arrange that in the outer array like this. This is L4 outer array, right? For the design 1, 4 combination. And this 4 combination is arranged by arranging the noise factors in L4. So we just take this out and transpose that back so we can have this orthogonal array. Then we can understand the output K, this 4 sample output, is the inference of the noise factors on design number 1. So this noise factor is in level 1, level 2, level 1, level 2, etc. Then we can apply the analysis of mean to come up the effect plot like this one. From the effect plot, we can get, okay, these compound noise factors, which is minus, plus, minus, which is the result from the previous slide. This combination will give us the lowest output. Same time, the second combination of noise factors, which we select these 3, the red circle, right? Like the effect plot. We select this combination in such a way the output will push it to the largest. So this combination, we call it compound noise factor level 2. This is how we get the compound noise factor. If you want to use 3 level, how do you do? In this case, the first level still the same, and the second level will move to the third level. So this third level is the same as the second level. But we add the middle level here, this level 2, where we make the compound noise factor work in the middle value. In the middle value, which means that the lower, the upper, the middle will be 0, right? So in this case, we add another sample where no errors at all. So we can have 3 compound noise factors if situation is required, such as if your output distribution is highly nonlinear, you might need 3 level noise factors. So how do we do if we use compound noise factors in the experimental design? The compound noise factor is a method of sampling which we only use 2 or 3 samples for each design. Like this one, for the cantilever beam, we are using the compound noise factor to have 2 compound noise. For design number 1, if you are using L9 by L4, we were using 4 samples, right? But now we only do 2 samples. The first sample is the compound noise level 1. The second sample is the compound noise level 2. Therefore, we can have 2 samples. Using these 2 samples, get the mean, standard deviation, and the SN ratio. This is how the experimental design works. Follow the similar process for the second design and continue, finish the design. You can have all the SN ratio for your control factors. The rest are the same. You are using response table, effect plot to find out what kind of combination for the control factors will give you the robust design. This is how it works in this case. I will explain that first, and then we'll ask you to work on this example. This was the original L9. And here, we were using compound noise instead. We were using L4, but now we only need 2 samples. First samples is a combination of the noise in such a way output will be minimized. CN1 is the combination of B1, delta H1, delta L2. And the compound noise 2, the combination will be this one, 2 to 1. So we apply this 2 combination to the first design here. Under the influence of the noise factors, this dimension will be different, right? So you can change the actual dimension and get what will be the corresponding stiffness under the influence of compound noise 1. Same thing, noise 2. The rest are the same. From these 2, you can mean, variation, and SN ratio. So from here, you can understand how many total number of samples you use for now. You use L9 and 2 compound noise, which is only 18 samples. Compare with the L9 by L4, which we use 36, 2 times of samples. That's the reason why compound noise factors can be used to reduce the number of samples and still keep the purpose of our sampling strategy. The purpose is to understand what will be the distribution of our output. Auto array, we do samples. We do several samples here, several samples there, but they are balanced and symmetric. But in compound noise, we only do 2 samples. One, which will get the largest output. Another one will give us the smallest output. From these 2 samples, we can have roughly the output range. Then we can have the mean, standard deviation, and also the SN ratio. Honestly speaking, we are not just using 18 experiments. Why? because we need to do some pre-study first. We need to do some pre-study to get the compound noise. We did one outer array experiment, 4 samples over here. From these 4 samples, we come up the compound noise. We use one outer array to get the duration of the noise factors. So starting from here, we can get the compound noise factor. Then for the complete experiments, we don't need to go through outer array for every design. We just need to use compound noise factors, which are only 2 levels for each design. But there are some restrictions, as I mentioned over here. There are some prerequisite or some assumption for using compound noise. First, you need to consider all the major noise. Just like the bathroom scale. The bathroom scale, we only consider 2 noise factors. We consider is type of floor and also the standing position. But there are manufacturing error too. For the bathroom scale, there will be a spring, 弹簧. And the spring will have a manufacturing error just like the cantilever spring we analyze. There might be some tolerance for the dimension. So you need to go through this noise factor first and understand what will be the major noise. In this case, we didn't consider inner and we didn't consider manufacturing tolerance. Why? Because the error of outer noise will be more important than the manufacturing error. So we consider all the noise, but at last, we only think these 2 outer noise are most important. That's the reason why I say you need to consider all the major noise factor first, including outer noise. In our classroom example, just for simplicity, just for the size constraint, I use 3 noise. In fact, in your practice, in your exercise, we use 4 noise, right? We consider the noise of the Young's modulus into our noise factors. And then we have a bigger outer array. We use L8. Since L4 is not big enough to accommodate 4 noise factors, so we need to go to L8. If you were using L9 by L8, the total number would be 72. It would be a lot, right? So there's a reason people used to be conservative. People used to consider not many noise factors. By using compound noise factors, you can consider more noise first. But from this major noise, you need to study the directions in order to consider the combination of the noise factors. If you don't know the direction, you can use analysis of mean on the initial design. Then you can have the direction of the noise factors. How about the third? The direction of the noise should be the same through the design range. The directionality of the noise factors will not depend on the setting of control factors. Why this is important? Why this is a requirement for the use of compound noise? For compound noise 1 and noise 2, and we assume this combination will make our stiffness, will make output to be the lowest. This one will make it to be the largest, right? And we use this combination for all the design in the inner array. And we assume these 2 directions or these 2 combinations will be the same, which means that, for instance, like design number 9, the compound noise level 1 will have the smallest output. Compound noise 2 will have the largest output. If the direction change, then this assumption will be incorrect, which means that if the combination of compound noise 1 in another design will not guarantee the output to be the lowest, then you have problem. Therefore, The third requirements to the application of a compound noise factor is you have to make sure the direction of the noise vectors will not change because of the change of control factors. If you are not sure, you can check again if you get the optimum design, and from that optimum design, you can apply another set of autoarray into the optimum design, and to analyze the direction of the noise vectors at the optimum design to double check if the direction is still the same. Okay, let's compare the use of compound noise factors and also the cross array design for experiment. We know that compound noise factor can greatly reduce the number of experiments, such as from L9 by L4, we can down to L9 by 2 compound noise. But you know, it's based on 3 prerequisites. And also at the beginning of the experiments, if we don't know the direction of the noise factors, we need to use one autoarray to understand what is the direction of the noise factors. But there are some drawbacks. The estimation is not accurate compared with the autoarray. Autoarray will give a more accurate estimation of SN ratio, but it's too expensive. Autoarray, too many experiments. Compound noise, cheaper, only 2 experiments. But the price of the cheap experiment is larger error. The SN ratio, the estimation of SN ratio will have a larger error. Since we only use 2 samples to estimate the mean and the standard deviation, certainly you can know only 2 samples, the estimation of the standard deviation will be less accurate. However, the most important thing is to determine which one is the best, not how best it is, or not exactly the output, the actual SN ratio. We only need to know the relative direction. Although we use different criteria, we use not that accurate SN ratio, but as long as we can compare the difference for different design, then the use of compound noise factor is still okay. The last one is, if you are talking about the accuracy, the autoarray still have some advantage. The autoarray will give a better estimation of the SN ratio. Okay. However, if you are have some constraint for the cost, it is still good to use compound noise factors. This is an example we worked on 2 weeks ago. In this example, we consider 4 noise factors, including delta B, H, L, and E. As we know that since we consider 4 noise factors, L4 is not big enough, so we need to go to L8. But in this case, L9 by L8, the total number of experiments will be 72. It is a lot. Let's try to reduce the number of experiments by compound a noise factor combination. Classroom example, we were using compound noise for only B, L, and H, right? Let's try to do the compound noise for 4 noise factors. Go back to what we just introduced. We need to know the direction for delta B, delta L, delta H, and delta E. How do we know the direction? We apply the autoarray samples to one of the particular design. Let's also try first one. So assume, let's go back to this one. I will suggest you to copy this page to, how do you copy? You use this one, 移动或复制, copy and click 建立副本, make a copy and select, move it to the back. And select OK, you will make a copy over here, right? So you will not mess up the original L9 by L8. but you can create a new experiment. And let's rename that. Rename into, say, L9 prompt, compound noise spectrum. Okay. From the first design, this is the first design, we apply a outer array, L8 outer array, to study the direction for delta B, delta L, delta H, and delta E. We only need one set of outer array. Okay, so we just want to apply this one, and let's try to copy this one, put it here. But remember, when you pass it, select it, pass it, 选择性贴上 select it, pass it, and you want to pass the value only. You want to pass the value over, and you don't want to pass the equation. You want to pass the value, and also when you pass it over, you want to transpose. You want it transpose, click transpose. So just copy the value and click transpose, and okay. Then you can copy the first set of outer array experiment to here, and it will look exactly like a orthogonal experiment for the noise factor. And this is the output due to the design number 1 under the influence of this 8 noise factor, L8. See? Right? So let's copy that over. If you have any question, please raise your hand. 那个嘉伟四处走一下，看看同学有什么问题。And let me try to make it look like a table so you understand we were working on this one. Now, I want you to analyze the inference, the directions for these 4 noise factors. You can do that by using analysis of mean from the response table and also effect plot. One. Okay, so this will be the response table. And the response table, level 1, you can use average if. It's better to have a double check which is the average of these 2 levels, and make sure the average of all the noise factors are the same. If they are not the same, which means that there might be something wrong during the type of equation. So right now they are all the same. Response table is okay. Then we can get the effect plot. Insert effect plot. Effect plot for the noise factors. As you can see that these 2 noise factors has a larger influence, right? Young's modulus and H will have a larger influence, right? And these 2 smaller influence. So you can understand that we should consider delta E, right? It is a strong influence. But due to the number of experiments, we kind of neglect delta E at first. But now we need to consider all the noise factors, all the manufacturing noise factors. But we want to use this direction to come up the compound noise. So once you finish that, you will know you can have the compound noise factor 1 and compound noise factor 2. So what will be the compound noise 1? So starting from here, you can insert circle the compound noise factor 1 will have an output. Okay, let's refill and use red as a circle. So this will be level 1. level 1, delta L2, and delta B1. So let's insert the symbol. So I don't need to type delta. And it is right here. Read delta, insert. So it will be delta, and from here, delta E, E1, and also delta H1, L2, E1. This is the compound noise number level 1. So once you get compound noise number 1, you should have compound noise level 2, right? This combination will make your output K to be the smallest. Same thing, the other combination will make your output K to be the largest. I already get level 1. I believe you should be able to get level 2. Then, after that, let's come back to the experiment over here. This is the experimental design. It was for L9 and L8. Now, we don't want to do 8 outer array. We will only want to use 2 compound noise. So let's get rid of the, okay, let's get rid of this one. Let's erase this 4. 选起来，把它删除掉，把这8个删除掉，我只留下2个。Click and delete. Delete, make the right cells move left. All right, it's become this. Only have 2 noise, right? 2 samples. And the first one, let's change it to compound noise factor 1. This one will be compound noise factor 2. I only want to do 2 samples. And these 2 samples is 2 combination of the noise factors. What kind of noise factors? Look at your result over here. This is our result, right? We get compound noise factor 1 over here. Let's copy that over so we can see. Let's put it here. All right, so we know compound noise 1 is delta A, E1, H1, L2, B1. 1, 1, 2, 1. So you need to change the combination in first level. Compound noise 1 is 1, 1, 2, 1. So here, L is upper bound. Plot 1, 2. Same thing for compound noise 2. It's very easy. Minus this will positive. Positive this is negative, right? So we know this level 2 will be, level 2 will be this one, and this is plus, and this one is plus. This compound noise array, we use 2 samples. And these 2 combinations for all the inner array. And for the first combination, we assume for each design under this combination, the output will be the lowest, smallest. On the other way, this combination of noise factor will make it to the largest. And then we have these 2 combinations, you can get the output. We can start over again. We are using equation to simulate the process only for simulation. So which will be E? E is this value, E. But E under the inverse minus 5%, which means that you will be actually 1 minus 5%, will be 95%, which means that the actual value of Young's modulus will be only 95% of the nominal value. E, B, E, but under the influence of noise, B over here, H, power 3, and over 4 multiplied by L. L is blocked. That's right. E6 它被挡住了，我用打的 E6 plus the arrow for L, this one. Okay, this is the equation. Oops, something wrong. All right. Yeah, I don't need this quote. Yeah, this should be right. 1.125. And I show you the trick, right? How to copy the equation over. I show you the trick. Since I want to make the control factors in all the column B, C, D, E. So for the column B, C, D, E, press F4, function key 4. 功能键 F4. Press again. We want to fix the column. B, fix the column. C, fix the column. Same thing for E. For noise factors, we want to fix the row 1, 2, 3, 4, because when we move to the second column, okay, but when we copy downward, we want to fix it at this row 1, 2, 3, 4. So for the noise factors, we want to fix the row number 1. Oops. 1 and 1. We use $sign to fix the row for the noise factors, $sign to fix the column for the control factors. And the reason we were doing that, because when we copy the equation to the right, see, it will correctly reference to the right combination of control factors and noise factors. Once you finish that, you will be able to copy the equation downward and get, if I just kind of modify the table, then you will get the mean, standard deviation, and also SN ratio directly. Right, let's double check again. Yeah, correct. This is the compound noise factor applied to the L9 outer array. So you can see, even though I consider 4 noise factors, you see, I still use 9/2 18 experiments. Unlike previous example, we were using 3 noise. Then for the closed array, we need L9/L4, 36. But if we consider 4 noise, we need to use L8 outer array, which L9/L8 will be 72 experiments. But if you are using compound noise factors, no matter it is 4, no matter they are 4 or 3 noise factors, we only use 2 samples, 2 combination of the noise factor, 2 samples only. So even 4 noise factors, total, I still only need 2 samples, which make it 9/2, which is 18 experiments only. Some of you might have different answer like mine, because we have different arrangement for the control factors. We have the SN ratio for the design. Now we want to analyze the effect plot for the control factors. This is the mean. We have 2 effect plot, remember? Okay. Plot, we have 2 response table, one for the mean, one for the response for the SN. So I change the value, the response table is still okay. Although we have different sampling strategy, but the key point is we are working on the SN ratio and the combination of the control factors. Yeah, so you can get the effect plot for your control factors. The next step is try to find the optimum design. And we go through two-stage optimization, remember? Right? So let's go back to our selection. What will be our optimum? No matter you are this plot or that plot, let's look at the SN ratio first. Let's try to find a combination that will give us the largest SN ratio. So B will be B3, H3, L3, and E1. So the optimum combination will be H3, B3, L3, and E1, which is the same. The same combination will give us the maximum SN. That's the reason we are using compound noise factor, right? We were using compound noise factor. We only use 18 experiments. However, we still have the same first stage optimization, like the original L9, L8, right? The original L9 by L8, the first stage optimization still have 3, 3, 3, 1, the same. And we were using compound noise factors from the smaller design, and we also have the effect plot. And from the effect plot, although it's different from the tendency, we know we should select B3, H3, L3, E1, the same. So we are using the same combination. From the first stage optimization, this is a combination, and what will be the SN ratio in this case? Let's try compound noise 1, compound noise 2, and this is the average output, and this is standard deviation, and this is SN ratio. Let's try to look at this number carefully. Let's see. 16.99. Is it bigger than any of them? Yes. 16.99 is bigger than any of the 9 design. And also this is the initial design, right? Initial design 16.25. So we are kind of happy. The SN ratio from the analysis mean is the largest. A similar problem raised here is the mean 0.89. It's not on the target. The target is 1. So we need to find the scaling factor. Remember? Again, how to get a scaling factor? Let's look at a curve. Assume this is the curve we have. So you can see the classification of these 4 factors become not as obvious. In our previous analysis, we are pretty sure B, L, and E are class number 3. But in this case, yeah, for the mean, there are some inference. But for the effect, these 2 are not that big inference, but some inference over here for the L. So next is several selection you need to do. You need to find 1 scaling factors. It seems E is the best selection because no inference on SN, but some inference on mean. As I mentioned before, E is not a good selection because E, Young's modulus, is a discrete variable. It cannot be changed easily. So you will not select E. Next, you should select either B or L. Which one will you select? Based on the manufacturing difficulty, we think that L is easier to adjust. B is not as easy. However, look at if we are trust this figure we have, it seems that B has smaller inference. So some might say, okay, how about select B as a scaling factor? Sure, you can try that too. What will happen if I choose B as a scaling factor? The SN ratio using outer array will have a bigger error. So the one using outer array, this one, is more accurate. However, since we want to save money, we didn't use L9 by L8. If L9 by L8, I believe your result should look like this. It is very possible if we are using compound noise factor, the estimation of the SN will be less accurate, will be not as accurate as you are using orthogonal array. That's the drawback. However, you can live with that because from this effect plot, you still have the same design. Now, the only problem here is the classification of the control factors. You might run into a problem about the classification. You might see L is more like type 1 because it has some influence on SN and also some influence on mean, more like type 1. Well, but you need to select one scaling factor. This looks like a good selection, but we cannot use this one because of the discrete variable. So we need to pick a second best. So you need to find the most suitable variable as the scaling factor because this is a nominal, the best problem. Some of you might select B. Since B looks better like type 3, you can try by yourself. What if we use B as a scaling factor? What happens if I use L as the scaling factor? These two are not as perfect as a scaling factor, but you have to pick one. If you are using L as the scaling factor, right? These two remain the same. Then you should change this variable. And we change this variable 52.1, okay, 997, and you can change to 52, almost the same, since we want to move the mean to average. However, why the result is different from L9 by L8? The reason is because of the sampling strategy. So that is the reason why I mentioned before using outer array will have a more accurate result. The only problem is too expensive, too many experiments. So we were using compound noise factor. The result is not as good, but usable and cheap, most importantly. But I want you to try, if you are using B as a scaling factor, what will happen? Now we want to change this value, right? We want to change this value. This is a scaling factor. We want to try an error for B. Let's try. 6.8, what happened? 7.5. Too big. 7.45. We can keep trying. Yeah, about 7.39, something like that. Well, somebody might get panic. Wow, what happened? I get two different designs. But let's look at the design. Which is better? Which is better? It depends on your problem. If you still remember, what is the design range for B? Design range for B is between 4 to 6.6. 6.39 is outside the range already, right? So it's really up to the design constraint. Is it okay for B to be as big as 7.39 since it is outside our design range? If you think it's okay, then it is okay. But if there's some hard constraint saying that the B shouldn't be bigger than 6.6, then you cannot use this design since it is outside the design range.